Today, we're diving into a trio of fresh AI papers that rethink the guts of modern language models, from attention and projection sharing to the tiny normalization scales hiding inside them. We'll look at a BrainChip study asking whether transformers really need 3 separate QKV projections, a ByteDance seed and Peking University paper on why scale vectors matter far more than their size suggests, and Parallax from Northwestern, Tilde Research, and the University of Washington, which pushes local linear attention toward practical large-scale training and fast NVIDIA inference. Let's explore the first paper, Do Transformers Need 3 Projections? Systematic Study of QKV Variance. This ICML 2026 paper by Ali Khayyam, Anusha Madan Gopal, and M. Anthony Lewis at BrainChip Inc. asks whether transformers really need separate query, key, and value projections. The authors systematically compare 3 weight-tying variants, Q equals KV, QK equals V, and Q equals K equals V, with optional 2D positional encoding to restore asymmetry in non-causal settings. Across 12 tasks, spanning synthetic sequence manipulation, vision, and GPT-style language modeling on Slim Pajama, they find that QK equals V is the best projection sharing design. In 300M parameter language models, it cuts KV cache memory by 50% with only 3.1% perplexity degradation, and at 1:2B scale, the gap shrinks to 2.48%, while downstream 5-shot accuracy drops by just 0.41 percentage points on average across HelloSwag, PIQA, ArcEasy, ArcChallenge, and Winogrand. By contrast, Q equals KV preserves training quality better than expected in vision tasks but gives no cache savings, while Q equals K equals V is too restrictive for language modeling, suffering a 25.4% perplexity hit at 300M scale. The study also shows projection sharing is orthogonal to head sharing. Combining QK equals V with GQA4 yields 87.5% cache reduction, and with MQA it reaches 96.9%, enabling much lower memory autoregressive inference. On 1:2B models, these architectural changes translate into measurable throughput gains on an A100, with QK equals V improving decode throughput by 4.4-5.3% and reducing peak memory by 6.5-6.9% versus standard QKV. Let's explore the second paper, Negligible in Size, Significant in Effect on Scale, Vectors in Large Language Models. ByteDance Seed and Peking University present a systematic study of normalization scale vectors in modern LLMs, focusing on RMS norm in Llama and Gemma 3. The paper shows that these vectors are tiny, only 80,640 parameters in a 1.3B Llama model, or 7.84 times 10⁻⁵ of total size. Yet removing them raises validation loss by about 0.028 under matched learning rate, and still by 0.015 after retuning, cutting token efficiency by roughly 1.4 times. The key theoretical result is that in prenorm transformers, scale vectors do not add expressivity because their effect can be absorbed into the following linear map. Instead, they speed training through a self-amplifying preconditioning dynamic on the effective weights. The authors then split normalization into input norm and output norm types and prove that weight decay should be applied only to input norm scale vectors, while it is harmful for output norm scale vectors that directly control expressivity. Building on this, they proposed 3 lightweight upgrades: branch-specific scale vectors for attention and FFN branches, dual-sided or dual normalized placement around linear maps, and magnitude direction reparameterization in Euclidean or exponential form. On 12B to 2 ByteDance Llama and Llama Mo models, trained on industrial scale token budgets with Atom W, Muon, and WSD schedules, the unified strategy consistently lowers terminal loss, often by more than 0.02 on MOE runs, with negligible runtime overhead of 1.04 times and memory overhead of 1.01 times. Let's explore the third paper, Parallax Parameterized Local Linear Attention for Language Modeling. Parallax, from Northwestern University, Tilde Research, and the University of Washington, rethinks attention for language modeling by parameterizing local linear attention instead of solving its per-token ridge system exactly. The paper starts from the test time regression view of attention and shows that local linear attention improves the bias variance trade-off over softmax attention, but is too expensive and numerically fragile for large-scale pre-training. Parallax removes the conjugate gradient solve and learns an extra query-like projector, R, that probes KV covariance, while also introducing a hardware-aware streaming kernel that reuses the same KV tiles as flash attention and doubles arithmetic intensity in the large context regime. On NVIDIA H200, the prototype decode kernel matches or beats flash attention 2 and 3 across batch sizes 1 to 2048 and context up to 32,768. In pre-training at 0 and 6B and 1, 7B, parameters on ultra-fine web with a Qwen 3 backbone, Parallax consistently lowers perplexity and improves downstream accuracy on Lambda, Wikitext, BoolQ, HelloSwag, PIQA, ArcEasy, ArcChallenge, Winogrand, OpenBookQA, and SciQ. The 0.6B muon run reaches 55.99 average accuracy versus 54.54 for the transformer baseline, and the 1.7B muon run reaches 62.45 versus 61.43. A key finding is optimizer architecture co-design. The gains are strong under muon, but largely vanish under Atom W, because muon increases the norm and alignment of the correction branch, allowing the covariance term to activate instead of collapsing towards softmax attention. That's a wrap on today's AI paper highlights. Thanks for watching.